from then on. And so that's our plot of electric field. Now, how do we get electric potential from that? Well, electric potential, VAB, is the delta V between R equals A and R equals B. Now, if I go from negative to positive, that's going to be an increase in electric potential. If I go from positive to negative, it'll be a decrease in electric potential, because I'm going with the electric field if I go from A to B. But if I go this way, then a positive charge, it's got to push, keep pushing on it, so I have to do work on it to move it to that spot. And so that means that there would be an increase in electric potential. So how do we get that from this picture? Well, the electric potential is equal minus the integral of E dot dr. And so this would be from R equals A to R equals B. So essentially what we're looking at then for the magnitude of this is just the magnitude of the area under this curve. And so sometimes it gets a little confusing if I'm going from B to A or from A to B, then theta is going to be different. But you also have that minus sign in there. So you have minus the integral from A to B. And so if I'm going this way from A to B and not from B to A, then this is going to be negative. So you have minus a negative, and then you have E times dr times the cosine of 0. But if you went from B to A, then this would be times the cosine of 180, because then you would be going this way against the electric field. That would be increasing the electric potential. But then you have the cosine of 180, and that would cancel out the minus sign and give you a plus sign. So what I'm trying to say is that these minus signs can be a little bit of a headache. So what I usually like to do is just kill them right here. And then I say, well, I know the area under this curve is the magnitude of VAB. And so then I just make sure that when I integrate this thing, I get a positive number. Okay, and so E then is going to be Q over 4 pi r squared, 4 pi epsilon naught r squared. And then we're going to integrate that over dr. And so what that will give us then is Q over 4 pi epsilon naught times r to the minus 1 divided by minus 1. That's going to be 1 over r. So you could write this as 1 over b minus 1 over a. Or let's do this as 1 over a minus 1 over b. Because I'm going to make this positive, okay? Because I'm killing the minus signs here. So even though I'd have a 1 over b minus 1 over a, that would be hit with a minus sign, which would be the same thing as just making this positive. This means kill all minus signs. Okay, and so that would be the difference in voltage, VAB. Then if we wanted to move a charge through that voltage, then the work that's done, move a charge a little q through VAB would be equal to Q times VAB. So this would be the work. And so that would be how much energy then that charge would gain in being moved from this point to that point against the electric field. And so that's the connecting link then. In the problems that we looked at before, we were saying that if we know V, we can get E minus dV dr. So this is, if we know V, we get E. But the other way is this way. Here, from Gauss's law, we know E. This means we can get B. And so we can work both ways with this, where the electric field is the slope of the voltage versus our curve, the negative of that slope. And so we can find the electric field from V using that slope relationship. But here, what we're looking at is the area under the curve. And so how much energy then do I gain if I move this charge, little q, all the way from infinity to the center of this sphere?
Zero.
I'm moving a charge, little q, from infinity to here. So how much work do I do? Is it related at all to, is it related at all to this work? Do I have to add something to it?
Is it instead of B is infinity?
Well, there's only charge out to B. So if I move this thing from infinity, how much charge is it seeing until it gets to B? Not seeing any charge at all. So there's no electric field to fight against. So there's no work done there. And then, got to push really hard to get to here, but then once I get to here, what is it from there? Zero electric field inside of here, because once we break through, and so to get this thing to the center is no different than moving it from there to there, because there's no electric field to fight against going to here, and there's no electric field to fight against to go to the center. So it's the exact same answer as what we got here for going from B to A. It's the exact same, because we don't do any work if there's no electric field to fight against. Then it's as if there wasn't anything there at all. Are there any questions about kind of looking at that problem, but kind of expanding on it a little bit? Yes?
We were going over with the tutors, and I think they said that if you have a conductor, for the Gaussian surfaces, you work from the core outside to the shell, you work from in to out. Is that correct, I think?
Well, it depends on what you want. If you want the electric field, then you have to set up 3 Gaussian surfaces. And so it doesn't matter what order you do it in, but if you want the electric field in here, you've got to set up a Gaussian surface that is there. And if you want to find out what the electric field is in here, you have to set up a Gaussian field that's in there. And so it's important that you see that these are flexible Gaussian surfaces, that this one can go all the way from B to infinity, this one can go from A to B, it's any value from A to B, and then this one can be any Gaussian surfaces less than A. And so to find the electric fields in those regions, you need 3 different Gaussian surfaces and 3 different Gauss's law calculations to get them. But you can get them in any order that you want. Any other questions? Okay, so what if we change this problem then, so that this is minus 3q. On the outer surface. Here, sorry, minus 3q. On this outer surface at B. So we keep everything else the same. Then, does that change the electric field up to B? No, it doesn't change the electric field up to B, because that's just going to still be Q over 4 pi epsilon naught r squared. But when we go for R greater than B, then what is my net charge enclosed? Negative 2q. So how's that going to change this? Well, it's going to be a negative electric field, and it's going to be twice as big. So if this is some value there, it's going to be that value doubled. So it'll bring it down to there. And then it'll follow an inverse square law like this all the way to infinity. So that's the way the plot will look if we had a minus 3 cubed, because the net charge enclosed is going to be minus 3 cubed plus q, which is minus 2 cubed. So what this is going to be then basically is the reflection of this curve extending out to infinity. So if this were extended out to infinity like that, it would look like that. So this would be double that at every point, that with a curve that goes from a negative value of e then out to infinity. So does everybody see how that has changed the problem? Is everybody clear as to what happened there? We have a net charge enclosed now that's equal to minus 3 plus 1, or minus 2. So that whatever this is going to be double that, but negative, and then decaying as an inverse square law all the way to 0 at r equals infinity. How would that change the work done? Is the work done going to be the same?
Yeah.
No, because we have to fight against a different amount of charge now. This is saying as we move in this way from infinity, we have to find the area under this curve too, and add that to the area under this curve. Question?
But wasn't this charge positive and it'd be a negative field?
Right, so the work done would have to be negative. You'd have to pull back on it. It goes, slow down, guy. You know, you don't have to push on it, you have to pull back on it. So that would be negative work. Yeah.
Do the equations for these tend to converge then? And like, is that something we'll have to look at? Because that's
Converge in what way?
in a way that the sum of the area underneath the r-axis is a number instead of infinity.
You here you have what's called a convergent infinite series.
Right.
So the area under this curve, even though it goes out to infinity, is a finite amount of area.
Are they always going to converge though? Or
They would have to converge.
Okay.
Yeah.
Okay.
Yeah, it would have to converge. And so this would be a convergent infinite series. You'd be integrating from infinity to r. But, you know, it's like if you take 0.1 and you add 0.01 to it, and then 0.001, and then 0.0001 to it, you have an infinite series that it converges. It would never get to 0.2, you know, even though you're adding an infinite number of terms. And so similarly here, you're adding every decreasing number of infinite terms, but that adds up to a finite number. And it would always have to be that way, otherwise it would be physically impossible for the object to move, because it would take infinite energy to do it. And then also, another thing that we've kind of brushed under the carpet here is that this is perfectly vertical. It's not going to be perfectly vertical, because in a real life situation, this shell won't have zero thickness. And so this shell is going to have a little bit of thickness to it, and where the charges are exactly on the shell, because they're discrete charges, means that if you look at this thing from a continuous point of view, there'd be certain places where the electric field would cancel. There'd be other places where it would go to infinity. And so we're smoothing out all of those local disruptions right near the surface where you've got these point charges that are separated by finite distances. And we're saying that it's approximately a vertical one, but that's not exact. And similarly here, this is going to have to be a smooth continuous function. And so do something that would round off just a little bit there. Otherwise, you'd have here, if you look for the value of the electric field, it's not, I mean, the value of the electric field is fine there, but you know, if you plotted the electric potential, which would go like 1 over r, then at that point, you'd have undefined slope. So those are things that we kind of brush under the carpet here by looking at the continuous case. Any other questions? Okay, well, next thing is wanted to look at how to, because we can do this, this comes in really handy sometimes because it's easier to calculate electric potential for a continuous charge distribution than it is electric field. And the reason why it's easier to calculate electric potential is that you don't have to worry about components of it. Remember, electric potential has no components. V is a scalar, not a vector. So you go, well, how do we make a vector out of it then? Well, it's because the slope has a direction. That the voltage itself is a scalar quantity. It doesn't have a direction associated with it. And so what we saw before then is that V equals KQ over R for a point charge. Or we could write this as Q over 4 pi epsilon naught R for V. So, how would we make that work then if we had, let's say, a ring of charge? Let's say that this ring has a radius A and a total charge Q uniformly distributed over the surface, over the ring. It's a one-dimensional thin ring. So we've got this positive charge, just like we did before with the electric field problem. But in this case, what I want to do, just to show you that this kind of works nicer, is to find the electric potential V of x, a distance x away from the center along the axis of the ring. So for a distance x along the axis away from the center of the ring, what is the voltage there? Now when I say the voltage there, what I really mean is the difference in voltage between there and infinity. So if I had a voltmeter here, then the ground side would be connected out there at infinity, and the hot side would be connected there, and you get this difference in voltage V between those 2 points. And so it's a state of voltage, but it's relative to the voltage at infinity. Okay, and so how do we do this? Well, if we know what a point charge's electric potential is, then we can say that dV is equal to dQ over 4 pi epsilon naught R, like that. And so R then is going to be the distance along this hypotenuse, and so that R will be square root of x squared plus a squared. And this will be our little dq. Now remember, our strategy for doing this before with the electric field was to take another little charge that was exactly on the other side and then cancel out the vertical components. And so this is something you may be tempted to do here, but it's completely not necessary and would be wrong if you did it that way. Because voltage is a scalar. And so that means that it's not going to have components that add or cancel. So we don't have to worry about any cosine theta stuff in here at all. And so what we can do instead is just say that v as a function of x is just equal to integral of dq divided by 4 pi epsilon naught square root of x squared plus r squared. But for every little dq, we have the same value of r. Because this one going over to there, this is going to be the square root of a squared plus x squared. That'll be that distance. And on the back side, square root of a squared plus x squared. Down here, square root of a squared plus x squared. So those are all constants and can be pulled outside of the integral. And so this is something I was seeing a lot of you doing when we did a ring problem before, is trying to integrate dq as like some lambda times dr d theta. And that's not really necessary here because all